The wrong PCB termination strategy can make your signal look good on one end, but end up messy at the receiver. So which one do you choose? Series, parallel, Thevenin, AC, or differential? Well, each one has its trade-offs. I ran the Sigrity Aurora Topology Workbench simulation on the same trace to see how each of these termination strategies performs. I'm Kirsch Mackey, an electrical and electronics engineering consultant. I'm counting down from number 5 to number 1 to see which termination strategy solves the most problems with the fewest trade-offs. But before I do the countdown, let's start with the base case. Whether it's single-ended or differential pair traces, when you don't have termination, you can get issues like ringing, overshoot, undershoot, blips in the signal, and slow settling times. When those happen, we have intersymbol interference, and that causes the eye diagram to close. That's what we're fixing. Now, on to the termination strategies. Strategy number 5 is AC termination. You put a resistor and a capacitor in series at the receiver. This blocks DC and it terminates AC. This is useful when DC loading on the line is a problem. However, the trade-off with this termination strategy is you're using 2 components instead of only 1 component. Also, the capacitor value you choose matters. If you pick the wrong value, your signal response slows down, or you can get incomplete termination. On top of that, you increase your cost, so you have the cost of 1 resistor and 1 capacitor. However, it comes in handy whenever you need to block DC. So use it when you need to block DC. Strategy number 4 is Thevenin termination. This is where you put a resistor divider at the receiver, and it also provides a bias voltage at the same time. This is useful when the receiver needs a defined common voltage. The trade-off with this strategy is you're using 2 resistors for each net across a wide bus that doubles the components on your bill of materials and increases the need for board space. So this DC termination strategy is useful for voltage biasing. However, the cost is 2 resistors per net, more power consumption, and a bigger bill of materials. So that's strategy number 4. The next 3 termination strategies are the ones you'll be going for the most often. Strategy number 3 is parallel termination. This is where you put a resistor at the receiver pin to the ground. This gives the signal a matched load. It reduces signal reflections and also sharpens the edges of your signal, and it opens up the eye diagram very cleanly. But there is a trade-off. You'll get continuous DC power consumption. If your design is power limited, this is not the right pick. The cost is only 1 resistor, but it also costs your power budget. Next is strategy number 2. We're almost at the end. Series termination. This is where you place a resistor at the transmitter or driver, and you choose the value to match the trace impedance and the driver impedance. It cleans up ringing without consuming DC power. However, the trade-off is a slower rise time at the receiver. For very fast signaling, this can cost you margin. The cost is only 1 resistor without a power penalty. Now we're down to strategy number 1, differential termination. For differential pairs, you put a resistor at the transmitter or driver on that leg of the differential pair. 1 resistor per leg. Each resistor will be half the total differential impedance. So let's say you have a 90 ohm differential impedance, you need each resistor to be about 45 ohms. For PCIe, USB 3, DDR, and other high-speed standards, the proper version is split termination with a bypass capacitor at the center tap to the ground. This handles any common mode signals that may come through from a mismatch in the differential pair. Something to keep in mind is that this center tap capacitor does not fix the common mode voltage problem. It just absorbs the effects of the problem, and the resistors don't fix phase mismatch either. So the cost is you need to use 2 resistors per differential pair plus the capacitor for split termination. Now that we've covered some termination strategies, here's a key takeaway. There is no single termination strategy that wins for every design. It depends on your driver impedance, your receiver requirements, your topology, and your power budget. The purpose of simulation is to test the choice before you commit to the PCB layout. So simulate first, route second, but you only need to route once. I'll see you in the next video.